I work in integrated systems. That concerns essentially the design of hardware and chips based on integrated circuit technology. If you look everywhere around you, there's chips in cell phones, computers, cloud in the routers, all the data infrastructure that we currently use today. And the heart of that are essentially integrated circuits, chips, which inside them have transistors, that communicate, compute, etc. And so if you look at the last 10 years, the capability of that technology has slowed down. We've rode a really nice ride in the 20th century for about 40 years. Everything has been getting better and nicer with this technology. And all of a sudden, the scaling slowdown hit at about early 2000s, where we've started seeing sort of the end of how well we'll be able to improve these devices. We're getting better performance from the chips as devices are getting smaller and smaller, and people have gotten used to expecting every generation getting better and doing more. But in fact, people behind the wheel are realizing that there's soon going to be an end. And the question becomes, how do you keep the thing going further and getting the performance that users expect, getting community to get better computers, better communication? And so there's essentially two ways, and my group is looking at both ways at the same time. And one is trying to say, okay, we'll use these devices until their very end, but we need to put some smarts back behind which algorithms, which techniques, and how we map down to use these transistors. Because there's a lot of overhead in the way people currently partition the design complexity. We're talking about millions of transistors being put in collections to work together. And as you're building up these circuits, there's overhead in performance that you're sacrificing for engineering abstraction to make essentially design easier. So what we're trying to do is go back and trim out that fat from the design cycle and understand how to better integrate the design layers so that we can bring in new and more powerful mathematical concepts and techniques that have been developed on sort of the theoretical side, and still based on these algorithmic improvements, improve the performance of the systems. They're designed, let's say, with CMOS technology, which is the workhorse of today's integrated circuits. Now, on the other hand, that CMOS eventually will die out. And what we're trying to do in parallel in understanding how the systems work, try to bring in some new promising device technologies. Researchers have already started working on a plethora of different switches, different transistor replacements, different types of fabrics through which you can communicate between chips and on chips. For example, instead of copper wires, people are looking at photonic interconnects, sending photons instead of electrons. In terms of transistors, people have looked at mechanical relays that now mechanically switch instead of electrically inside these chips, and spin a bunch of other physical mechanisms. But what really needs to happen is to understand how do you take these very exotic devices and put them in collections of tens, hundreds, thousands. How do you grow them to the complexities of million or billion devices that are currently on our sophisticated CMOS chips? And in the end of the day, what performance advantage will they give you? If you're about to embark on a 10-year quest to bring this new and promising device all the way into the mainstream fabrication and build these billion device systems, you better know up front that there is a system level gain to be had. And unfortunately, when you look at the landscape in the past 10 years, most of what people have been doing is really focusing on optimizing that one device and making a perfect paper or research announcement about it, but very little understanding how that device can now become a more powerful collection of similar devices and what real gains at the system level will be made. And as an artifact, if you look at sort of the national nanotechnology initiatives, none of these nano devices have really made it big to compete very heavily with existing CMOS technology. The reason is that people haven't managed to look at the collection of devices yet and prove that it's better than what exists in CMOS. And so my group really is focusing largely on early modeling of these devices, understanding what design principles and sensitivities these devices have, trying to build early prototypes that will showcase the power of some of these technologies. Not all of these technologies are actually very promising. Once you do a few steps into the circuit and system design, you pretty quickly see that some devices are hopeless, then you also pretty quickly see that some devices have a really untamed potential, even if they were discarded at the device level. A good example is this MEM relay switch, which our collaborators at UC Berkeley have done. This is an electromechanical switch that the fundamental advantage at the sort of the switch technology level is that when you turn it off, it does not leak current, unlike CMOS transistors. And that is one of the key fundamental problems with CMOS technology overall. And the Berkeley researchers have figured out ways to integrate them to be very small, and a number of other schools have followed that as well. But what was largely missing is how do you put these collections of seemingly slow devices together to still compete with very fast CMOS technology. And my colleagues at Berkeley and UCLA and our group at MIT have figured out ways to do that, for example. And all of a sudden, you have something that was an underdog kind of incumbent that was trying to come up, and we found ways to make that technology be very appealing and competitive with CMOS, but at the system level, not at the device-for-device level.